Hi everyone. So today we are going to be covering section 6.7 in the textbook, which is physical applications. So this section is kind of a hodgepodge of various different applications in physics, specifically very engineering focused physics problems. If you do go on to take a physics class, you will see many more examples where calculus will come into play. But this is to kind of give like a brief overview of a couple of different other problems that you can also use calculus to solve. So the problems we're going to be talking about today, we'll be dealing with the mass of one-dimensional objects, so strings or chords or things like that, especially if they're changing how dense they are. We'll also be talking about how much work it takes to do certain things, the amount of work it takes to pump tanks full, so pumping problems they're called, and then finally we'll talk about force on dam problems. So if you have a dam, how much force you are experiencing on this dam. So it would be how strong you'd actually have to make your dam. So first thing we're going to be talking about is these mass of one-dimensional object problems. So we know that mass is given by the density, so this is just how dense something is, times the volume of something. So if you have something that's all the same density and you know what its volume is, you can just use this formula in order to figure out the mass of an object. However, in our case, this density is going to be changing. And this is where integration is going to come into play. So this is changing. In general, we are going to denote this density as rho of x. So what this means is that we need to come up with an integration formula in order to figure out what our mass is now going to be. So if we look at a picture, which I have here, and we take our one-dimensional object that we're looking at and we break it up into these smaller and smaller chunks, similar to what we've been doing with surface areas, with volumes, with lengths, all of these things. Break it up into smaller and smaller chunks. Well, then we can just approximate the density of one of these really small chunks by just a constant density, right? Because it's not going to change too much from one really small end of our object to the next. And so what this means is that we actually get this formula here for a one-dimensional object where mass is going to be equal to the integral from a to b of rho of x dx. Great. So let's just jump straight into an example for this. So in this problem, we have a 2 meter long string. I'll call it rope, I guess. Rope. Which starts at a equals 0 and goes to b equals 2. And we have a density function of rho of x equals 1 plus x squared kilograms per meter. So what this means is that at x equals 0, so at the left end of our rope, we are going to have a density of 1, right? Because that's what happens when we plug in 0 for this rho function. So 0 to 2. At the one end, we have density of 1, and then at the other end, we have a density of 5. That's what happens when we plug in 2. So as we go along this rope, it's going to get thicker and thicker and thicker, or more dense and more dense and more dense. And so that means that we can't just take some specific density and multiply it by the volume, we actually have to use this integration. So in particular, looking at the formula that we have, we get that the mass is equal to the integral from A to B. Well, in this case, it would be from 0 to 2, of our rho of x. So 1 plus x squared dx. If I do the integration, right, this is going to be x plus 1/3 x cubed, evaluated from 0 to 2, plugging values in. This is going to be 2 plus 8/3, which is equal to 14/3 kilograms. We always have to, in these types of problems, be careful that we have the right units. So our units of our density function are going to be kilograms per meters. Our A's and B's are also in meters. So when we multiply kilograms over meters times meters, the 2 meters are going to cancel, and we're just going to be left with kilograms as our units. So 14 over 3, 14 over 3 kilograms. Okay, so that for these types of problems will be the formula that you use. Right, as I mentioned at the beginning, this is pretty eclectic of a lecture, so we're just going to go straight on to a different example, which is going to deal with work. So the formula that we have for work is going to be work equals force times distance. So it's how much effort you need to apply multiplied by how long of a distance you are actually applying this. However, similar to the previous problem, if we don't have constant force or we don't have constant distance, we need to introduce integrals. So in this case, we're going to be dealing with variable force. So this is going to be changing depending where we are with respect to distance. So a picture that we have of this here is this. So basically all that's going to be happening is that at certain x values, you're going to be pushing this box more hard than you would be pushing it at other x values. So you're just not always applying this constant force to the problem. So very similar to our mass function, actually, we have an integral function for work, as work being the integral from A to B of our force function, force of x dx. So often the units for this, and I think all of the units in the problems I assigned for this, for work are in joules. Joules as our units, which are Newton meters, and our force units are going to be newtons, which is denoted by N. The joules is denoted by a J. So just make sure you are keeping track that your force is in newtons, but if it is, then your work will be in joules. Okay, so let's jump into another example for this. So we're going to be talking about springs for this example. So we have something when we're dealing with springs called Hooke's law. Hooke's law says, and this makes sense, is if you have a spring, the farther you are away from equilibrium, the harder it is to stretch, right? So that's a great example of times you would need to use this problem. Because if you are stretching a spring right in the beginning, it's pretty easy. You're applying less force. However, at the end, you have to apply a lot more force to move the spring the same amount. So in particular, in math terms, Hooke's law is going to be given by f of x equals kx. Okay, so the kinds of applications you might see for this is it's generally relatively easy to tell how much force it takes to stretch a spring out. There are instruments that can do this, and we are interested in figuring out what this K value is for our spring. Okay, so the specific problem we're going to look at for this is, let's say that we have some spring and we have it stretched out 0.1 meters and it takes 10 newtons to hold it right there. So a force of 10 newtons to hold spring at 0.1 meters. Okay, so a first question we can ask is, according to Hooke's law, what is our K going to be? So in this case, we can just plug everything in, not using any calculus, and we can get that 10 is equal to K times 0.1. Dividing both sides by 0.1 is going to leave us with a K equals 100 newtons over meters. Great. So then we can ask questions like, well, how much work do you need to actually compress this spring? And let's do that. So how much work was needed to compress a spring uh, 0.5 meters? Okay. Well, we have our integral for our work formula. We now have our force function, right? We know what our K is, and so we can take all of this and plug it all in to figure out what our work is actually going to be. So in particular, for this problem, we are compressing 0.5 meters, so we are starting at equilibrium at 0, and going compressed, which is negative to negative 0.5. In general, for these types of problems, compressing to the left will lead to a negative x value, and stretching will lead to a positive x value, which is just a convention that we hold so that we can distinguish the two directions. All right, and we also have our work function, which is going to be just 100x dx. So plugging things in, we get that this is going to be 100x squared over 2, evaluated from negative 0.5 all the way to 0. Plugging in negative 0.5 is going to give me a 1/4, so I'm left with 100 over 8 joules, which is equal to 12.5 joules. Okay, so that's how much work it would take in order to compress a spring this amount. Now, let's say that we have our spring stretched out a bit and we want to know how much work it's going to take to stretch it out a bit more. So this is problem D from the book, just following the lettering of the book. Spring is at 0.25 meters. How much work does it take to stretch it an extra meter? Well, now we are no longer starting at 0. We're no longer starting at equilibrium. We're starting at 0.25. So in this case, our A is going to be 0.25 instead of the 0 we had in the last example. So we have the integral. We're moving from 0.25. We're stretching it out an extra 0.1. So that means we're going to end at 0.35. We have the same integral we were talking about before with 100x dx. The force function for these spring problems is only going to change based on what your K is. The x part will always stay the same. So we can get the same integral of 50x squared evaluated from 0.25 to 0.35, which I don't want to square 0.35. That sounds really nasty, but if you actually go through and do this, you're going to get that this is 5.625 joules. Which is really interesting, right? It took almost half as much to go from 0.25 to 0.35 as it did to go from 0 to negative 0.5. So you can see it is getting a lot harder as you go along. You need a lot more work to go this extra 0.1 meters. Okay, so shifting gears to just a different type of problem. The third type of problem we'll be talking about today are what are called lifting problems. So the very standard example you have for this is you have a chain that you are lifting up and you would like to know how much force it's going to be taken to lift up. The important thing here though is that your mass is changing over time, right? As you reel this chain up off the ground, less and less of it is going to be hanging, and so it's going to take less and less force in order to lift up, say, the second half rather than the first half. So for these lifting problems in general, force, I see what the problem was. Fix that. Force is given by mass times gravity, and with all of these problems where we do introduce calculus, this mass is changing. This is gravity. You might run into some problems, specifically in a physics class, where gravity is changing. This would happen if you're working on very large things where, say you have a rocket and it's getting farther away from Earth. Gravity is going to be changing depending how far away you are from Earth. But we're dealing with things close to the ground, so gravity change is negligible. Actually, in this class, you can just assume that gravity is equal to 9.8 meters per second squared. So no matter where you are, that's about what gravity is. The formula now that we have for this is going to be given by the integral from 0 to L, where L is going to be the height we're looking at, of rho. This is another rho, so this is density, times g, which is gravity, or 9.81 meters per second squared, times L minus y dy. This L minus y times the rho is going to give us the mass of whatever we have left. So density is a mass over in this case, meters, and this L minus y is going to be meters, so that's going to leave us with the mass. So this force equals mass times gravity does line up with our new integral formula for this. Okay, so just jumping straight into an example for this, which they drew a nice picture of in the book. Let's say that we have a chain, like I was talking about before, that we are lifting up 10 meters, and we would like to know how much force this is going to take. So in particular, we are lifting chain 10 meters. Now, if we come up to this formula, there's one extra piece of information that we need to know that we don't have, right? It's this rho or this density, and that is given to us for the problem. So we also have that our rho is going to be equal to, 1.5 kilograms per meters. In general, you might be given the mass of the thing you are trying to lift up. You can always find density by taking the length divided by the mass. But in this problem, we are given the density, actually. So this 10 is going to be our L, and so we have, just plugging everything into this formula, the integral from 0 to L becomes the integral from 0 to 10 of 1.5 times 9.8 times 10 minus y dy. Just pulling out the rho and the g, I'll just keep these in variables, rho and g, 10 minus y dy. Taking integrals, rho g, we get that this is 10y minus 1/2 y squared, evaluated from 0 to 10. Plugging everything in, we get, again, rho is 1.5 times 9.8 times, well, the zeros won't matter because that will make everything 0. So we just have 100 minus 1/2 times 100 squared, which when you do the algebra, get out your answer. This is going to lead us to approximately 735 newtons or joules of work. Great, yeah. So this is going to be our final answer for this problem. So the next thing that we're going to do is, let's just say we add a bucket, which is the bottom of this figure 6.74. So add a bucket, and let's say that it weighs 15 kilograms. Now, what's really nice about this is that this bucket isn't going to be decreasing the weight as we go up, right? So it's going to have this constant amount of work that it needs in order to lift things up. So in particular, we have work is equal to m times g times y, where this is the distance lifted. I think I misspoke before. This last problem we were finding the work, not the amount of force needed, because we are integrating over a distance, and so that means we are indeed multiplying force times a distance, which is going to give us work, which is why our final answers were in joules. So this is work problems instead of force problems. Apologies for that. But, right, so we have this formula for work, which is just force times distance lifted. This bucket isn't changing anything over time, so we don't need to use integrals to figure out how much work this is going to take for the bucket to be lifted, just disregarding the chain at this point. So the amount of work is going to be 15 times 9.8 times 11, which is approximately 617 joules. So we know how much work it takes to get the chain up. We know how much work it takes to get the bucket up. We can add these together to get the total amount of work. So in particular, we have total work being 2,352 joules, approximately. I rounded off these answers to avoid decimals. So that is just one more application that we have for integrals. So the next two that we're going to be talking about are slightly more complicated examples. They're definitely not extremely complicated by any means, but the first of these two that we're going to talk about is work required to pump things. So if you have a tank full of liquid and you'd like to know how much work you're going to need or how much energy you're going to need to pump all of the liquid out of the top of it for some type of project, you will need to use integrals to solve this. And so we're going to go through the process of how you do this. Okay, so let's just pull up a picture here. So similar to kind of what we've been talking about this entire chapter and what we've even talked a bit about today, is we're going to break up this container into smaller and smaller and smaller cross sections, and then we're going to look at the work needed to lift out one of these cross sections, right? So we're going to make it so that instead of dealing with volume, where it takes less work to get things out on the top than it does on the bottom, to just this flat surface where it takes the same amount of work to get anything out of there, right? The amount of work just depends on how tall we have to move upwards. And so if we have these flat cross sections, then we don't get this discrepancy between needing a lot less work for things at the top versus things at the bottom. So if you work through this, we get the formula that the work, and this is again specifically for these pumping problems, which I'll write. Work is given by the integral from a to b of rho times g times a of y times d of y dy. So rho, again, is going to be density. Often we're going to be dealing with water in this class, which has a density of 1,000 kilograms per meter cubed. That's how we define these measurements. So that will be often what this is. This g is still going to be gravity. This a sub y is going to be a cross-sectional area. So coming up to this figure 6.7 right here, we can see that these cross-sectional areas are going to be given by circles. So in this case, we're going to have pi r squared. But we can see, right, the area is varying depending on the height. So this is going to be a function of our y value or our height value. And then finally, dy is going to be how far it needs to be lifted. And then finally, these a's and these b bounds are the least y value, the least y value and the greatest y value. So the thing with these problems that's very different from the other problems is that we get to pick where we put the axis. Almost exclusively, what's going to end up happening is that we are going to put the axis system at the bottom of our tank. Things will work out really nicely. This dy is just going to be how tall it is minus how far up you are. The a value is going to be 0. The b value is going to be how tall the tank is. However, in physics, it doesn't matter ever where we define our coordinate system. As long as you are consistent with these formulas, we could have our coordinate system way out here for this problem, where our 0 is going to be like halfway up the tank. That will work fine. So what you have to do when you're starting these problems is always just make a choice where your coordinate system is. I would almost always recommend the bottom of your tank. And then we go from there. So this a sub y is based on this coordinate system you picked. This d sub y is based on this coordinate system that you picked. Okay. So let's jump into an example of how to do this, which I think I have a picture of. I cannot remember. Nope, no picture. Okay. So let's say that we have an upright cylindrical tank. It's full of water, so full of water. Right, which means we're going to get a density of 1,000 kilograms per meter cubed. G still 9.8, we're on Earth, meters per second squared. We know some more things about this tank, right? We need a height and we need a radius. So we know that the radius is going to be 5 meters. And we know that the height of this is going to be 15. H equals 15 meters. Okay, right, so as I said before, first thing we should do is we should pick a coordinate system. And I'm just going to pick it at the bottom. So this is my x direction, this is my y direction. Okay, and we really only care about the y direction because that's the only thing we're integrating with respect to. So we have a couple pieces of information for this. We have our density and we have our gravity. So there are 4 different things we now need. We need to know our a's and b's, and we need to know our cross-sectional area, a of y, and we need to know our distance function, this d of y. So starting with a's and b's, well, our lowest y value, because of how we set this up, is going to be 0. That's the bottom of the tank. So a is 0. Which means that b is going to be the topmost, y value is going to be 15. Okay. Now we need to figure out our cross-sectional area, a of y. In this very specific problem we're looking at, right, the areas of cross-sections aren't going to change as we go up or down. So we should expect that our a of y actually won't depend on y for this problem. If we look at this and we look at some cross-section right here, it's going to be a circle. And specifically, the circle's radius is always going to be 5 meters. So our a of y is always going to be 25 pi r squared. Okay. And the final thing we need to know is our distance function. So if we're at a specific y value, how far do we need to be lifted up? So distance of y. So if we're at this y value right here, well, we are y meters up from the bottom, and we need to go 15 meters. So we're at 15 minus y as our distance function. So plugging everything in, we get that this is the integral from 0 to 15 of rho g 25 pi and then 15 minus y dy. Simplifying a bit, this is rho g 25 pi. Those are all just numbers. They don't have anything to do with y, so we don't need to integrate them. The integral of 15 is 15y, and the integral of y is a y squared over 2, so minus y squared over 2. And these are evaluated from 0 to 15. So after you plug in the 1000 for the rho, the 9.8 for the g, the 15s for the y, you're going to get your final answer for this, which I didn't write down from the book, but you're like one step away from actually having the answer for this problem. We are going to do a slightly more complicated example as well, because this one didn't have these changing areas. So on the surface, it's going to seem like a very similar problem, but we'll see as we go through why it's going to be different. So our problem is now a sideways tank, half full. And we will get to see my very lovely drawing skills for this one. So we have okay, it's half full of water again. And we have a spout, which is going to just come right out of the middle right here. And we would like to know how much work it's going to take to pump out all of the water out of this tank. So we need to know a couple of things about this. We need to know how long it is, and we need to know the radius, right? So we know that this tank is 20 meters long, and we know that it has a radius of 5 meters. Okay, so the big difference from this problem to the previous problem, 10 meters, not 20 meters. 10 meters. Just so my work matches up with the work I have written down. Okay, big thing between this problem and the other problem, right? If we're looking at a cross-sectional area of this, and I'm slightly down from the center, this area is going to be different than what I am at the top, right? As I get lower and lower down, what's going to end up happening is that I'm going to have smaller and smaller areas because the width of this rectangle for my cross-sectional area is going to get smaller and smaller and smaller. So what we need to do is we'll need to figure out some function in terms of y for this. What we need to do for this problem right now, though, is we need to pick a coordinate system. This will be actually one of the cases where it is easier to pick a coordinate system not at the bottom. It would definitely work if you picked one at the bottom, but let's pick one right in the middle instead. So we have our tank, and we're picking this cross-section right here where this is going to be our coordinate system. So we have y's and we have x's. Now, the reason we're doing this is, what this means is that our values are given by really, really nice functions, right? We know what the function for a circle is. So in particular, this is given by x squared plus y squared equals 25, right? R squared is 25. That's what this curve is in our coordinate system. So if we're going through this, and if we are trying to figure out a of y, well, in our coordinate system, if we're at some y value right here, we have this extended rectangle out, which I kind of drew in this picture right here. So we need to know what this length is, L, and then we'll multiply it by 10 to get our area. So this is going to be L times 10, where L is just this length right here. So this is our L. The nice thing about having a formula for our curve, though, is that this L is actually going to be our x values. So these are x values. Or I guess 2 times x values. 2 times x values, right? So what we know for this is we know that y is equal to the plus or minus square root of 25 minus x squared. We are in the negative part, so I'm going to take the negative part of this. So y equals negative square roots of... we are interested in the x values in terms of y. That's my bad. It's very symmetric for this problem since we're dealing with circles. So we have x equals plus or minus the square root of 25 minus y squared. We are going to take the negative part of this, the positive part of this. I'm all over the map today. The positive part of this, because we're dealing with lengths, and so we want to know how far along this way we are. If we took the negative of this, we would have negative lengths, and then you'd have negative areas, and that's something we don't want. So we have x equals square root of 25 minus y squared. And so this length function is just given by 2 times our x value. It's how far along we are in the x's, and we have to go in both directions. And so our area function is 10 times the square root of 25 minus y squared. Okay. We also need to figure out our d of y, so how far up we need to go. D of y. And we also need to figure out a and b still. These are much easier than the area function. So d of y, if we are at this y value right here, means we have to go up this amount right here, which is negative y. Oh, I am very sorry. I'm messing this up. This spout for this is actually at the top for this problem. So we have some spout up here. So we are trying to lift the water up through the top. Okay. So we need to go up negative y to get up to our origin. And then we need to finally go up an extra 5 to get to the top. So what this means is our d of y is 5 minus y. So at a y value of negative 1, so a bit down from the middle, we're going to have to go up 6 meters to get out. And finally, our a value, which is going to be our lowest value down here. We know we have a radius of 5, so a is going to be negative 5, and b is going to be 0. So taking all of this, plugging everything into our formula, we get that this is the integral from negative 5 to 0 of rho times g times 20 of 25 minus y squared times 5 minus y. Okay, dy. So the important thing to note with this, which is going to make this problem much easier, is that if we're looking at the integral of 25 minus y squared from negative 5 to 0, right? So what we're going to do is we'll take this part and expand it out. The second part we'll be able to use u substitution on because we have a y squared and a y on the outside. However, for this part, we can't use u substitution. So we're trying to figure out the integral of negative 5 to 0 of 25 minus y squared. But if you remember back to calculus, one of the things we talked about was the act of geometric integrals, right? So integrals are the areas under curves. And so if we look at this, what this actually is representing is this area right here. Right? This is geometrically what this integral is going to mean. So what this actually is 1/4 times the area of a circle with radius 5. But we know what that is, right? We know we have formulas for circles. Circle with radius 5. So this is pi r squared over 4, or pi times 25 over 4. Right, so this allowed us to deal with this part of our integral where we expanded out and we were just left with a bunch of constants, the rho times g times 20 times 5 times the square root function. The other part of our integral is we'll also have the integral of negative 5 to 0 of the square root of 25 minus y squared times y. Again, I'm just leaving out the constants. We can add them back in after we've taken all of these integrals. You can always pull constants out when you're multiplying them, when you're dealing with integrals, and then put them in later. So what we would like to do in this case is we would have a u equals 25 minus y squared because we have our y on the outside. So when we take the derivative of what's inside of our function, what's inside of this square root, we're going to get a y out. So in particular, we get that du is equal to negative 2 dy. And we also need to, not that we can, we have to change the bounds of the integral. So we have y of negative 5. Well, plugging in negative 5 squared will give us a 25, giving us a u value of 0, and a y of 0 will give us a u value of 25. So taking all of this new information, plugging it all in, we get that this is the integral from 0 to 25 now of negative 1/2 square root of u du. Okay. We can then go through our standard process of figuring out what this is going to be. And it makes sense that there's a negative because there's a negative in front of this y right here that I didn't include in the constant. So it makes sense that we're getting a negative answer from this because we'll have a negative to cancel with this. But going through this, this is just the negative 1/2 times 2/3 times u to the 3/2, right? I added 1 to 1/2, divided or multiplied by the reciprocal, evaluated from 0 to 25. So, right, just going back to what we were talking about originally, we were trying to evaluate this integral that we have right here. We talked about how to evaluate the part that leaves us with a 25 minus y squared using a geometric interpretation. We also talked about the part that has a y times the square root of 25 minus y squared, which we used a u substitution for. So what in the end we're going to get, just putting this all together, is we're going to get a rho times g times 20 times 5, because we have a 5 there, times whatever this first integral was, so times 5 times pi over 25, pi times 25 over 4, and then adding in the second part of the integral, if we just call this a right here, we get rho times g times 20 times negative a, because we do have this negative up here from our original problem. So if you plug everything in, you plug in 1,000 for rho, you plug in 9.8 for g, you figure out what this a is going to be, which will not be very pleasant because you'll have fractions in it. We're going to get that this is about 20.2 million joules. And that's your answer. So that is how much work it takes to pump all the water out of the top of some tank half full lying down on the ground. All right. So we have one more application problem for this, which is a force on dam problems. So as we were talking about before, we want to break this problem up into a way that we can, instead of having pressure, in this case, be higher on the top and bottom, we'll break it up into really, really small chunks that we can then integrate over in order to figure out our force. So for this problem, what you need to know for this problem is that the force acting on a infinitely thin strip of a dam is just going to depend on the height you are above the water, so it's how much water is pushing down on it, and it also depends on the area of this strip. Right, so the farther down you are, you have more and more force acting on you. You can think about this if you go to a swimming pool, and as you go farther and farther into the deep end, down into the water, right, you can feel more and more force on you. So that's what's happening here, just on a large scale. So it's why we need to integrate, is because there's a lot more force happening at the bottom of this dam than at the top of this dam. And so we integrate in order to get the total amount of force acting on it. So we have the formula, force is equal to 0 to A of density times G times A minus Y times W of Y dy. Okay, so let me just talk about what this means. Force on dam problems, you will always put the y-axis on the very bottom. It never makes sense to put it anywhere else. Almost always, I guess. In this class, we'll just talk about putting the y-axis on the bottom. So as before, rho is the density. G is gravity. This A minus Y is just how far underwater you are. Where the A is the height of the dam. So you can think about it, right? If this dam here, we're in this coordinate system here, has a height of A, and we're at some point down here. Well, we're Y up from the bottom, and so we are A minus Y from the top, which is where the A minus Y comes from. And then finally, this new function, which is W of Y, and this is the one that you have to work to figure out. This is the width of a cross section. So very similar to the pumping problems where you had to figure out area. In this problem, the width is just going to be given by this width right here at some certain value of y. So for example, if you had a rectangular dam where the width was never changing, this width function would just be some constant, right? It'd be the width of the dam. But in problems like this, and we'll actually do a problem exactly relating to this picture right here, our width is changing. So we need to use a function for it. And this will be a very similar process to the last problem that we did, where we will introduce our coordinate system and we will use functions of the edges in order to figure out what this width is. Okay. So let me pull up the example we have. Oh, there it is. You can scroll over enough. Okay. So we are dealing with a trapezoidal dam, so it's skinny at the bottom, thicker at the top. That is 30 meters tall, 20 meters at the bottom, 40 meters at the top. Okay. So just going through this formula we have, we know that our A is going to be 30 because that's how tall it is. We're saying it's filled with water, so rho will still be 1,000 and G will still be 9.81. So the only piece of the puzzle that we don't have now is this W of Y function, this width of the cross section. So I want to know, if I'm so far up the dam, how far across is it? That is what the W of Y means. So what? So taking this and just drawing a picture. Let's just put the coordinate system smack dab in the middle of the bottom. So we have 10, negative 10, and 10 there. It's extending up. And these points are given by 20, 30, and this one by negative 20, 30. Right, so this still makes it 40 meters across on top. 20 minus negative 20 gives me 40. And we know that these are going to be straight lines there. And then this is going to be 30 because it's 30 meters tall. So if we think about it, and we think about what the width actually means in terms of this coordinate system, we have some y value we're interested in. And we're interested in a width right here. Width. Well, similar to the last problem, the width is going to be 2 times the x value. Width equals 2 times my x value. So what I'm going to do is I'm going to take this line I have here, I'm going to figure out a formula for it where I get x's in terms of y's, and then that is going to meet my w of y. Okay, so this is a line, and we know how to find the formulas for a line, right? We can find the slope using these 2 points, and then we can take that, figure out our b value in order to get our equation of a line. So as a reminder, right, slope is rise over run. So we have a 30 minus 0 rise. We went up 30. And we had a run of 20 minus 10, which if you do the math and simplify, this simplifies down to 3. So we have y equals 3x plus b. We can take this coordinate that we have of 10, 0, plug it in order to solve for b. So we have a y value of 0 equals 30 plus b, which implies that b is going to be equal to negative 30, excuse me. Negative 30. Okay, so we know our function in terms of y is 3x minus 30. However, right, we want a function w of y, so we want a function in terms of w, and we want this to be equal to x, because this is going to be how we figure out our width. But we can rearrange this, and we get that y minus plus 30 over 3 is equal to x. So now we can take all of the information we have. We now have our width function, which is just 2 times this function we have down here. We have our a's, we have our rho, we have our g, and we get that this is going to be the integral from 0 to 30 of rho times g times y plus 30 over 3 times 2 times 30 minus y dy. Okay, so this right here, I wrote it slightly out of order, is w of y, and this right here is just a minus y. Okay. So pulling constants out, we get that this is equal to rho times g times 2/3 integral of 0 to 30 y plus 30 minus y dy. Foiling this out, rho g times 2/3, we get a negative y squared, looking at the last terms, negative y squared. We get a positive 30y looking at the first times, and a minus 30y looking at the last term, so that's going to cancel out. And finally, looking at the inside terms, we're going to get a 900, so plus 900 dy evaluated from 0 to 30. Now this is in a polynomial form, which we know how to take integrals of. So rho g times 2/3 of negative 1/3 y cubed plus 900y evaluated from 0 to 30. Plugging all of the numbers in, we get that this is dealing approximately 1.18 times 10 to the 8th newtons, right? So just under 1 billion newtons worth of force. So, right, you can see dams have to be very, very strong to actually withstand the force behind them. Okay, great. Thank you for listening. I will talk to you all in the future.